Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Go ahead and raise your hand if you did not get a red mark for today, the 24th. Let's get going right away because we've got a big day and a shortened class period. And so we can use a given exponential function. We saw from our reading question an exponential function is called exponential because the variable, the independent variable, is up there in the exponent. And that's what makes it an exponential function instead of having my variable down in the base the way we do with the power function. And so the function above gives the number of subscribers in millions for cell phone subscribers in the year T. What value does the function give for the number of subscribers in the year 2005? If we're given a function rule, we can simply evaluate my function rule for the given time value T equals 2005, and that will give us the value of S. And so in context, S equals 125.5 times 1.129 all to the, and then I just put in my value for T into my equation everywhere I see in T and work it out. It's just that now my independent variable, my T value, is up in the exponent when I'm dealing with an exponential model. So I think this is a job for our calculator on the home screen. We don't need to go through graphing this or anything like that because we're just doing a single problem. I'm just going to go to the home screen and evaluate that. So I'll go 125.5 lag and 1.129 all to the, and in my exponent I'm going to do 2005 minus 2001. Now we know that that's just 4. If you don't have an 84 family calculator, make sure you're putting parentheses because you want your entire exponent to be the 2005 minus 2001. Awesome. And so it looks like our evaluation yields a prediction of $203.901 penguins percent. What would a label on this be? What would a label on this be? Ethan?
Subscribers.
Subscribers, absolutely. Subscribers. And we also need to be careful from my picture. It looks like this is in millions of cell phone subscribers. And so not $1 million, but million subscribers. And so it looks like my model predicts about 203.901 million subscribers. Go ahead and raise your hand if you already had that prediction. So we already had 203.901 million subscribers. Way to go, you guys. That's awesome work. Thank you. Let's take a look at another. This is also an exponential function. How can we tell? My independent variable, x, is up there in the exponent. And so when your independent variable is up in the exponent, that's an indication you're dealing with an exponential function. In this case, we're talking about the value, v of x of my car, x years after I bought it. And it's given by the function, v of x equals 32,000 times 0.87x. And I saw many of you, in trying to figure out when the value v was equal to $10,000, set up a correct equation. What equation did you have for that? Jen?
10,000 equals 32,000 times 0.87x.
Absolutely. Jen set my v of x function, right? 32,000 times 0.87 to the x equal to that constant, $10,000. And we were trying to figure out how many x years since I bought the car, right, does it take for the value v to equal $10,000? This equation is correct. However, at this stage in our lives, we don't have a means to solve algebraically for x. We're going to learn, but as of yet, we can't solve this algebraically for x. So what do? Well, we can get a graphical approximation for this value of x by writing, right? By writing in my y equals menu each function. So I could go ahead and put my original function v of x in for y1 in my y equals menu, my constant function, my second function, call it y sub 2, in my y equals menu, and then mess around with a window to see where they intersect. That will be when my value v equals 10,000. So everybody, let's do this on a graphing calculator. So everybody, please go to the graph. We'll clear out our existing y equals menu. If we have a plot 1, then we want to go ahead and up arrow to highlight the plot 1 and turn it off, right? If it was already shaded, you want to make sure your plots are off so they don't interfere with our graphing. So we'll go ahead and make sure your plots are off, and let's enter our original function, v of x, in y sub 1. So everybody, let's go ahead and enter 32,000 times 0.87 to the x. There's my exponential function. Remember, my variable x is up in the exponent. That's how I know it's an exponential function. And let's enter a second function, a constant function. Call it y sub 2. That's my $10,000. So we want to see when v of x equals $10,000. In order to do that, I need to get an appropriate window. And so I see that I've got 32,000 from my reading question. There's my initial value of the car. And so I need to make sure my window goes beyond our standard negative 10 to 10. I'm going to go ahead and set my window manually to make sure I have a big enough window to see the picture and the function behavior. And so for my x window, X stands for the years after I bought it. So maybe to get a nice picture, I know we can't go back in time, though sometimes we might wish we could. I'll go -5 to 20 just so I can get a nice picture. For my Y min, I can't have a negative value of my car, although there are a couple cars that I had in high school and college that I might consider a negative value. But I'll go ahead, just in the interest of getting a good picture, I'll go -5,000 up until, and 32,000 was your initial value of the car, so I'm going to go up to 40,000 just so I can get a little bit beyond. Okay, so I'm going to go -5,000 to +40,000. And if I don't like that window, we'll change it. So I'm just going to put that for a guess and check and try to get a good picture. So if I don't like it, I'm going to change that. So I'll go ahead and see what kind of picture that does for us. By pressing graph, it looks like my v of x exponential function is showing up in blue. And then my constant function is a horizontal line, right? There's my constant function showing up in red from the original equation that Jen told us. Does my v of x function, right? Does my value of my car decrease as time goes on? Yes, it does, and that makes sense in the context of the problem, right? So as soon as you drive off the lot of the car dealership, right, your value of your car depreciates. It goes down as the age of the car increases. So it looks like we have a good picture. Graphically, we can estimate how many x years it takes for the value v of x of blue to equal 10,000. We'll do that using our built-in software and a calculator. So everybody, please do this to remind yourselves. Second trace is the calculate menu. Which option do we want? We want the fifth option for intersect. So let me grab a screenshot of that. We want the fifth option for intersect. Remember, the calculator asks you for first curve, so press enter to tell the calculator, yes, that's the first curve. Second curve, press enter again to tell the calculator, yes, that's the second curve, and then a guess. It looks like there's only one point of intersection, so I don't need to toggle back and forth with my left or right arrow keys. Sometimes you do need to. So I'll press enter a third time for a guess, and voila! The calculator cursor will jump on at the point of intersection and tell us the x coordinate 8.352 about is paired with the y coordinate 10,000. So it looks to me like we've got our approximation. It looks like after about 8.35 years, and it asks for the nearest tenth, so we'll say after 8.4 years, about 8.4 years. So after about 8.4 years, the value of your car has depreciated to $10,000 from $32,000. Kind of sad. Kind of sad. Raise your hand if you already got that. So did anybody do the second calculate intersect already? That's great, because we don't have a means to solve that algebraically. We can only solve graphically at this time. Later in the unit, we'll determine how to solve that by hand exactly. That's pretty cool. All right. Finally, discuss with your partner how you can determine from looking at an equation if the function's a power model, right? A power function versus an exponential model. An exponential function like the first two. Quietly decide with your partner how you can tell whether it was an exponential function like in Bellwork 1 and 2, as opposed to our power functions from last unit. Then share with the class of my colony. So go ahead. How can you tell it's exponential? What was different about those functions?
Oh, instead of being like on the regular, that would make sense.
So suppose we have two different function rules, f of x and g of x. What's the defining attribute then of an exponential function? How can I identify based on looking at its equation that it's going to be an exponential function? What about the equation lets you know that it's going to be an exponential function? Ben?
If it's the variable is in the powers base.
Yeah, absolutely. If that variable is up in the exponent, then it's going to be an exponential function. And so if we consider a power model like back in our unit 1, right, parent functions, y equals x cubed is a power function, right? Y equals x cubed is a power function. So f of x equals x cubed is a power function where my defining attribute is my variable is a base and my exponent is the constant. Switch the position of those, and then you're dealing with an exponential function. G of x given by 3 to the x uses the exact same components. It's still a base and an exponent. But now we've got my base as a constant, a positive constant, and my exponent is my variable. My variable x is up in the exponent. And so this is an exponential model. This is an exponential model where I have a constant base raised to a variable exponent. That's how I remember that it's exponential, because my variable is up in the exponent, as opposed to a power function. A power function, my base is the variable and my exponent is the constant. So this is a power model versus an exponential model. That's pretty sweet. Thank you, Ben. All right, let's go ahead and take care of our homework check then. So at this time, I'd ask that you give yourself credit for those who completed on assignment number 0. We've already turned in our review assignment with the substitute. Go ahead and give yourself credit for those you completed on assignment number 0 out of 7. And if you did your reading questions 9-1, 9-2, and 9-4, then you're eligible for a 5th point. I'm going to pause the recording now while we do the homework answers, and then I'll resume it when we get to our content objectives. Thank you, ladies and gentlemen. So we're going to recognize properties of exponential functions and create and apply exponential models for either growth situations or decay. We'll also contrast that with what we already know about linear models that we've seen back in Unit 2. First up, let's go ahead and take a look at an introduction problem. Using the graphing calculators, again, let's suppose that the number of fruit flies n during a week-long experiment after t days into the experiment is given by n equals 24 times 2 to the 0.62t. We can answer all kinds of questions like, what's the initial value of fruit flies present in your little 2-liter bottle when you start the experiment, right? Determine an appropriate window and make a graph, so we'll use a grapher for that. How many fruit flies are there after a given number of days? And then how long does it take for the fruit fly population to reach a particular number? So let's go ahead and in our graphing calculator, let's go ahead and consider the initial number of fruit flies. And it looks like the initial number of fruit flies, right, is how many fruit flies there are when the experiment starts. And so how many days have passed when the experiment starts? Well, 0 days have passed right when the experiment has started. And so this is the same as determining the number of fruit flies n at the time t equals 0. And so to do this, we don't even have to make a graph. We can just evaluate my function rule, kind of like we did in the Bellwork number 1, and determine the number of fruit flies n after 0 days. So we'll plug in 0 for t and work it out. So that's the same as the number of fruit flies after 0 days have passed in the experiment. We know that any positive base b, any non-zero base b for that matter, raised to the 0 exponent, right, is equivalent to what? 1. And so the second half, 2 to the 0, is simply 1. So it appears as though the initial number of fruit flies present in my 2-liter bottle when I start the experiment is 24. And that's not dollars, right? It's not percent. That would be 24 flies. Let's determine an appropriate window and then graph my function. So for this, we will need our grapher. So we want to go to our y equals menu and clear out that old function. Everybody, please do that at this time. So we'll clear out our old functions. Flag. And we're going to enter our new function, 24 times the base 2 to the, and up in your exponent, if you have an 83 plus model calculator, you need to put parentheses up there. If you're in the math type, then you'll be up in the exponent. We need 0.62x Here's my variable button for t. And we'll go ahead and enter my function. We know this is a week-long experiment, and so after X days, we want during my week-long experiment, we want to go ahead and get some good X values, some X values on my window to represent that. I'm going to go ahead and still, I know I can't go back in time, right? Though sometimes we want to, I'm still going to put a little negative value just so I get a nice picture of my axis. So maybe I'll start -2, and I'll go up a little bit past, maybe till 9. And so -2 till 9. If it's a week-long experiment, that encapsulates from 0 to 7 days. We also want to change the Y window. Y in this problem stands for N, the number of fruit flies. And so I know 24 were present initially. What's going to happen to the fruit fly population as time goes on in this experiment, do you think? What do you think is going to happen to that number? Sydney? Increase. And so we want to make sure that we've changed our window. It's not going to work with -10 to 10. We need to go 24 and then bigger. And my guess is, since we're asked about values later in the problem, like 400, that we need to go bigger than that. So let's go ahead and take a window and manually adjust it. Let's maybe go -200, and then let's go up to 1,000. Now, I don't know if this is a good window. Right? I'm just going to do a guess and check and see if this is a good window. And if it is, then I'll take a screenshot of it. So there's our fruit fly population, and they're growing and growing and growing. And look what happens as time goes on. The number of fruit flies is increasing at an increasing rate. And that's a defining attribute of an exponential growth model as well. Awesome. So I think that window's okay. That does a nice job. So I'll go ahead and take a screenshot of our window. And now we can answer some questions like, how many fruit flies are there after 4 days? Well, just like number 1, we could evaluate my function rule by plugging in 4 for t. But since we have our graph, let's practice with our trace feature. So once again, once you're from the graph, on the graph, you can press trace. Where is that? That's top. Toolbar, 4th button, trace. And then X value of concern, we want to trace when t equals 4 days. So everybody do trace, 4, enter. After doing trace, 4, enter, voila, the cursor will jump on the graph at the number of days X equals 4 and pair it with the corresponding N number of flies Y. It looks like about 133.895, so that makes sense in this problem to say about 134, would we say? About 134 flies? Awesome. And lastly, after how many days does the fruit fly population reach 400? And so this, again, as Jen suggested earlier, we can write an equation that sets my n equals equation to 400, right? And then we have to figure out what x value produces that. We don't have a means for solving, but we can still solve graphically, right, using our calculator. So our original equation would be the n function, which is 24, times 2 to the 0.62x in this case. We want to see when that equals, right, when that equals my red constant function, 400. In our graphing calculator, we can go ahead and let that be y1. Our second function, call it y sub 2, a constant function, let that be y2. And let's go ahead and graph on the same window. Everybody, in your y equals menu, let's add the second function, y sub 2, the constant function, 400. Graphing in the same window produces, that's what we're looking for, the point of intersection, when n equals 400. And how do we get that? Well, like we did in our Bellwork, we can do second, calculate. The fifth option is intersect. First curve, enter. Second curve, enter. And then because there's just one intersection point, I don't have to toggle left or right before pressing enter a third time. And voila! The cursor will jump on the calculator at the point of intersection. It appears as though it takes, what does that say? 6.55 days, so after about 6.55 days. population of fruit flies reaches that 400 number. Right, and becomes a swirling mass of black cloud inside my 2-liter bottle. So we need to open it up and let them out. Fly, be free. Don't open up in here. Awesome. All right, so as a result of this introduction, we can contrast exponential growth and decay models with what we already know, like about linear functions. So let's review linear increase and linear decrease. We know from our regular algebra 1, y equals mx plus b, or now in advanced algebra, f of x equals mx plus b, that an increase, a constant increase situation can be modeled with my linear equation f of x equals mx plus b. And if it's increasing, we know we'd have a positive m value, a positive slope. And so recall that b is my start value, 0 comma b is my y-intercept. So if I had a b value here on my y-axis as my start value, I could then, with a positive value of m, represent a positive value of m is a constant increase situation, and I'd have a increasing line as I move along from left to right. If you're a math man or math woman, you jump on the line and walk along from left to right, you'd be climbing up as you move along from left to right. Contrast that with decrease, where my slope is negative versus a positive slope, and now you can still have some start value b on the y-axis. But now, as I move along from left to right, my function values will be decreasing. Right? Will be decreasing. So if you're a math woman and you hop on that line with negative slope, with your skateboard, you'd be sliding down the line as you move along from left to right. And bust the math at Ollie, because that's how you roll. We can now contrast that with exponential growth, right? Exponential growth versus exponential decay. Now we're always going to have positive base b's, bless you. From your reading question, you saw that a is my initial value, and b, right, base b is my percent remaining, my multiplier, right? Every x value that goes by, b percent remains of the previous amount. And so let's go ahead and see what this would look like as a picture. If a is my start value, it's still my y-intercept. And so this time on my y-axis, I'll go ahead and label a on my y-axis. And if my value of b is greater than 1, like the cell phone subscribers 1.129, right? If my b value is greater than 1, then I'm going to be exhibiting exponential growth. And we're going to have like the cell phone subscribers graph or like the fruit fly population. So what will that look like? It'll look kind of like this. And notice how in an exponential function, right, as time goes on, as you continue moving to the right, the rate of increase itself increases. It's getting steeper and steeper at a quicker rate as you look farther to the right on the graph. Versus b values that are in between 0 and 1. This is like the value of my car, right? As time goes on, that was the 0.87. 87% of the previous year's value existed as each year went by. And so this is an example of exponential decay. We'll still have some initial value a on the y-axis, but now we'd be dealing with a picture that exhibits exponential decay. So we're decreasing as time goes on, and doing so at a decreasing rate. Awesome. So after you get your general parent function for exponential growth, that is b values greater than 1, versus exponential decay, that is b values in between 0 and 1. Notice how b is always positive here. Now we can go ahead and apply it to some real-life applications. So let's suppose that you're dealing with strontium-90. That's a radioactive isotope that has a half-life of 29 years, right? 29 years. This means that in each 29-year period, half of the strontium-90 decays and half remains. Suppose that you initially have 1,000 grams of strontium-90. We can answer questions like, how many grams of that original sample remain after 6 half-life periods? We can determine the number of years in 6 half-life periods, write a recursive formula, an explicit formula, and finally a function for any real number x number of half-life periods. So let's go ahead and use our letters here. Our first one asks us to determine the number of grams of strontium after 6 half-life periods. And so we can consider this just through inspection and thinking about the problem. Remember, a half-life, right? A half-life period is the number of years it takes for half of the initial quantity to be present. And so let's see. After 0 half-life periods, I have my full amount. So after 0 half-life periods, I have my full amount, that is 1,000 grams. Then after 1 half-life period has gone by, that's 29 years, after 1 half-life period has gone by, I have half of that initial quantity present. So how many grams will be present after 1 half-life period? You can call out. 500. Got on the recording. 500. Right, grams. And we need to go all the way to after 6 half-life periods, so after 2 half-life periods, 3, 4 half-life periods, 5, and finally after 6 half-life periods, and that's our final answer that we want. So we're trying to determine the number of grams that remain after 6 half-life periods. So let's keep going. After 500 grams, another half-life period passes on down to 250 grams. After another half-life period, down to 125 grams. Another half-life period down to 62.5. Oh, lucky guess. 31.25. And finally, the answer we're looking for is the number of grams after 6 half-life periods have passed. So that would be down to 15.625. 15.625. Decimals are hard. Math's hard. Just kidding. I love math. I'm in a good mood every day. Awesome. B asks us, how many years is that? Well, if each half-life period was 29 years, then all we need is 6 half-life periods times 29 years. Each is 120 plus 54, 174. Is that right? 174 years? Awesome. Lost. And I think I need to do that. We want PDFable, Ethan, to go along with our class recording. We want PDFable. Awesome. So letter C asks us to write a recursive formula. A recursive formula for A sub n, the number of grams of strontium that will remain after n half-life periods. Great review for geometric sequences, where we have a constant multiplier as we move between successive terms, as opposed to a constant sum or difference as we move. Notice how we multiplied, right? To get from one term to the next, we multiplied by something. What did we multiply by to get from one term to the next in every single pair of successive terms here, right? What were we multiplying by to move from one term to the next? Mason?
I'm lost right now.
Well, let's take a look at our original table. That represents the number of grams after n half-life periods. As you move from one term to the next, what do we multiply by to get from one term to the next? A half, absolutely. So in my recursive formula, my multiplier to the previous term is going to be 1/2. Let's go ahead and write that. Remember, recursive formulas are easy to recognize because they've got our brackets connecting the two parts. We need our start value. In this case, I'm not going to use a sub 1 as my start value. In this problem, it makes more sense to use a sub 0, the initial value present after 0 half-life periods have passed. So I'm not going to do a sub 1 here. I'm going to do a sub 0, the amount in grams after 0 half-life periods have passed. How many grams is that? How many do we start with?
1,000.
1,000. So 1,000 is a sub 0. Now we need our rule, a rule that gives us the current term, called a sub n, based on the previous term, right? What did we do to the previous term? A sub n minus 1? Well, Mason told us we multiply it by 1/2. So half of the previous term will give us the current term. Matab?
Wait, so why don't you do a sub 1 instead of a sub 0?
That's a great question. Okay, so Matab asked, why don't we do a sub 1 instead of a sub 0? And as I look at the context of this problem, where we say we start with 1,000 grams, for me, it makes more sense to begin this rule at my start value, my initial number of grams present. My initial number of grams present was 1,000 grams, and that was after 0 half-life periods have passed. And so in this problem, it makes more sense to start with the initial amount present as opposed to the amount present after one half-life period has passed, because that's already 20 years into the problem situation, 29 years into the problem situation. I want to start at t equals 0. Kind of like when we start the fruit fly experiment. How many fruit flies were initially present? Well, that would be the number of flies n after t equals 0 days have passed, right? That was the 24. This will connect nicely to our value of a in our model, and that a occurs when x equals 0, not when x equals 1. It's my initial value, my y-intercept. Great question. All right, so let's go ahead and finish it out. How can we rewrite that as an explicit formula? Recall my formula for geometric, that is constant multiplier, constant ratio multiplier. We could use a geometric formula in general, would be g of n equals g sub 0 times constant ratio r to the n power. But for us, we're writing a formula not for g of n, but a sub n, right? When are we doing a sub n? And a sub n equals a sub 0, that is my initial value present. How much was that? That was my 1,000 grams. So 1,000 times my constant multiplier to the n. In this case, my constant multiplier, right, we already found 2. What's my constant multiplier? Luke? 1/2. Guys, check it out. Here's our exponential model. Here's our initial value, right? A sub 0, the y-intercept. Here's my constant multiplier, my ratio r from geometric sequences last. And if we write this as a function now, a function that gives the amount of strontium remaining after any real number of half-life periods x, I'm going to go ahead and call that function s of x. Careful how you say that, Ethan. S of x, which gives the amount of strontium after x half-life periods have passed. That will be a times b to the x, where a is my initial value, my y-intercept 1,000 grams, times my constant ratio, or my base b in this case is 1/2 to the x. So my function would be s of x equals 1,000 times 1/2 to the x, where my initial value a is 1,000, where go gadget arm, my base b percent remaining is 1/2. 50% remains after every x half-life period passes. My percent remaining is 50%. That's pretty sweet. Okay. Our second and final objective for the day is to write an exponential model that fits the data. That's called regression. So anytime you see that R word, right, regression, that means use the built-in software on your graphing calculator to generate an equation. So when you see regression, you're not doing it by hand, you're using the graphing calculator. For us to do that, we need to remember how we use the stat menu. So everybody, the table gives the percent of sunlight present at various depths as part of an ocean. Use exponential regression to find an equation that models the given data. So it looks like we're given the percent of sunlight that reaches a depth in meters beneath the surface. And so what's happening to the amount of sunlight as our depth increases? As our depth increases, right, less and less percent of the sun's rays are reaching you. That makes sense, right? So let's go ahead and enter this in our graphing calculator. Recall that we can enter real-life data into the lists in my stat menu. So everybody, let's go ahead and go stat, edit. And we're going to enter our x's in list 1 and our y's in list 2. So everybody, we're going to go ahead and label our x's. We'll put our x's in list 1 and our y's in list 2. So everybody, if you have data in your lists, you're going to up arrow to highlight the list title, press clear, right, and down arrow, and that will clear out your data. And then you want to go ahead and enter your x's in list 1 and your y's in list 2. I just erased all mine so I could show you how to clear it. So I'll re-enter mine and then we'll catch up. Take a minute and make sure you have the same number of entries in your x's and your y's so we don't get a dimension mismatch error. We want to make sure that we have all of our ordered pairs lining up. And we want to make sure that Mr. Fritz hasn't, with his fat fingers, messed up entering with the decimal places. So 10 by 7, 1.15. We're good? Are we good? Awesome. So we've entered our x's in list 1, our y's in list 2, and now we're going to go ahead and make a scatter plot of the data. So for a scatter plot, we want to display those ordered pairs as points on the xy coordinate plane. In order to do that, we need to turn our plot 1 on. So we go to y equals, and now we're going to take away our fruit flies and clear that out. And we're going to up arrow to highlight plot 1 before pressing enter to turn it on. So we're going to turn on plot 1 by up arrowing to highlight it and press enter to turn it on. Now our plot 1 should be on, which pairs x values from list 1 with y values in list 2. However, we won't be able to see that plot unless we change our window to match the data in the table. So what do? We manually change my window so that my x values, right, are bounded on the left and right by x min and x max, respectively, and my y values are bounded below and above by my y values. And so we need at least to the left of 0 and greater than 50, so I think I'm going to go negative 10 to 60. Oh, lag. X scale 1. Now let's consider a good y window. My y is percent of sunlight that reaches the depth. So my percent ranges from 0.001 very small rocks up until 100. So it looks to me like I'm going to go a little bit below and a little bit above that. Maybe I'll go negative 25 and I'll go 110. So I know I can't get a negative percent, but I'm trying to get a nice window, so I'm going a little bit below. Is this a good window? I don't know. I'm going to go ahead and see what it does for us. If I don't like it, then we'll change it. Whoa, it looks like our points shrink towards 0 very quickly, don't they? And that makes sense in the table. It looks like after 20 meters, we're already down at 1.15%. And so the percent of sunlight shrinks very quickly. But it's also important to note that my meters are going by tens here, not by 1 meter, they're going by tens. Awesome, so here's our scatter plot. Now we're going to go ahead and generate a model. A model is an equation that best represents that data. So how do we do that? Well, we also use the stat button. Here we go. Stat, calculate this time. And do we want fourth option, linreg? No. Do we want fifth option, quadratic regression? No, we want exponential regression. So where's that? I don't see it. I don't see it. Scanning, scrolling, voila. Option 0 is exponential regression. XReg for exponential regression. Everybody find that. So we're going to go ahead and do exponential regression. Enter, and then the commands are exactly the same. I like to store my regression equation in the y equals menu. You don't have to store it. But if you do want to, whether you're using an 83, 83 plus, 84 family calculator, you can store it by pressing variables, y variables, function, y1, and by telling the calculator to store it in y1, you don't have to worry about copying down decimals inaccurately, right, or typing them in a calculator wrong. And I have fat fingers, and so I'm going to mess up if I try to type all those decimals in there. If you have an 83, right, then you can just put the same buttons, vars, y bars, function, y1, enter, right after your xreg command. All right, a final enter, and voila! The calculator spits out values of b for a and b in my exponential model, y equals a times b to the x. Let's go ahead and write this down. So it looks like my model is given by y equals a times b to the x, where a is about 107.941 times b to the x, where b is about 0.79396 all to the x. This is an exponential model because my variable is up in the exponent. Everybody see that? My variable is up in the exponent. I can now, right, use this model to make predictions. What's the initial value? That's a. That's the a in a times b to the x. It looks like 107.941 is the initial value. That, again, is from a model. It's not exactly 107% because that would be more than 100%. However, my model is doing the best it can to match this real-life data. The percent remaining comes from my base value. Remember, my base in between 0 and 1, like 0.79, represents decay. the amount of sunlight is decreasing, right, as your depth increases. And so we've got exponential decay. It makes sense that my base B value, my percent remaining, is in between 0 and 1. So 0.7939, that would be what percent remaining? That is about 79.4% remaining for every 1 meter I go down. About 79% of the previous sunlight value exists. So every 1 meter in depth, every 1 meter your depth increases, you expect 79.4% of the previous sunlight amount to reach. Does that make sense? Awesome. Okay, let's do one more model and then we'll do closure. Because of our 2-hour release, we're almost done. So let's go ahead and use exponential regression to generate one more equation for the amount y of an investment after x years and answer these questions, and I'll round out our discussion today. So everybody, let's go ahead and do the same thing to practice. Here we go. I'm going to go ahead and in my stat menu, I'm going to enter my new amounts. Guys, make sure you're careful with your amount present now. It doesn't go by ones or by tens, and so it's irregular. Everybody, you can up arrow to highlight your list and then press clear before down arrowing, and that clear out your list. I'm going to go 2, 3, 6, 8, 9, and then enter the corresponding amounts. 3, 6, 7, 7, 9. Watch your decimal places. So I want to make sure that you match up to 3, 6, 8, 9, 37, 19, 27, 6, 9, 1, 2. And my calculator rounded, but that's okay. If I highlight over the thing, it'll show that it kept the places. Did I mess up? All right, we're going for it. Generate an equation for the amount y in dollars in the account after x years. So here we go. Where would you go to do that? Everybody do it. Stat, calc, expreg. That's the 0th option. I'm going to store it in bars, y bars, function, y1. I'm going to calculate, and I'm going to get a model. Now you don't have to store it. Just to get your model, you can just press enter and don't have to worry about the bars business, but I like to store it. Awesome. How much was invested initially? That's my A value. $3,500. And I can't think of a better color than green for that initial money. What's the annual interest rate as a percent? Well, recall my equation was y equals 3,500 times 1.025 to the x. Is my base B greater or smaller than 1? Well, it's greater. By how much? 0.025, which is indicating what percent increase? Looks like 2.5. And so this is 2.5% greater than 100%. So this is 2.5%. And we get that by moving the difference between my base B, percent remaining, and 100%. So that looks like 2.5% greater than. How much is in the account after 20 years? Well, that can be a straight eval question. So how much is in the account after 20 years? That would be y when x is 20. Everybody, let's do that. And we can do that on home screen, so you don't have to worry about the window. And in the interest of time. So I'm just going to do a straight evaluation, 3,500. 1.025 to the 20. Voila. looks like about $5,735.16. And what questions do you have about our exponential regression? Jen? Pardon? Number 2 was the initial value. That's the a in my equation. That's the a in my equation, y equals a times b to the x. Awesome. All right, guys. So we've got our closure now. In the interest of time, we're going to do this together. So you're not going to work with your partner and then share on the whiteboard. We'll do this together. Everybody, we need to make sure we get this in the last 2 minutes. So for a linear model, we know that we have constant increase versus constant decrease. For what values of m? Well, m is my slope, and so positive values of m represent linear increase versus negative values of m represent linear decrease. Contrast that with an exponential model, where now my base b determines exponential growth versus exponential decay. So my 2 categories, growth and decay, are determined by my values of b in my exponential model. B is my base or percent remaining. Growth occurs when my values of b are greater than 1. We saw with my cell phone subscribers 1.129. We saw with my money investment 1.025. When b is greater than 1, we're going to experience exponential growth. Versus decay, those are positive base b values that are in between 0 and 1. So 0 is less than b is less than 1. We saw that was like my value of my car. My base b was 0.87, right? 0.87. Exponential decay. My strontium, 0.5 or 1/2 was my base b. And lastly, go to that term. What's the difference between power function and exponential function? That is x cubed versus 3 to the x. In an exponential function, the variable is up in the exponent. So the variable is in the exponent in an exponential model. Great work today, you guys. I'll go ahead and stop the recording now, and we'll post this for our YouTube channel.